8.3 is on trig integrals or trigonometric integrals. And there's a special form or type of form we look at to simplify and reduce powers of trig identity or trig functions to simplify. And there's some formulas they derive. They're called reduction formulas. Those actually are called reduction formulas, as I mentioned before. But what really I want you to be able to do is apply the trig identities. So this is the concept of the derivations of those formulas. And that's really more important. You can always just apply a formula. But what's most important is that you can use or apply a trig identity, show that you can, basically, to reduce these powers in this technique. So this is the most important concept here, really. So these are the main, in doing this application, not deriving the formulas. So these are the main identities we're going to be using, and specifically these, solving for the powers, of course, for sine, cosine, secant, and tangent. And then this is considered a power reduction, like the power reduction formula we will be using when you have something like this. So first we'll look at this example. So let's evaluate the integral of sine to the fourth x dx. And remember that's, of course, sine x quantity to the fourth, but that's the abbreviation we like to use. So if you tried to use any sort of u sub right now, I mean, it's basically not going to work because you're going to pick sine to the fourth. If you picked it to be sine, then you end up with a cosine. There's no cosine in there. Okay, so you could try it. What you need to do, or what we do, is we want to reduce the power. So we want to basically take, say, w to the fourth, something like that, and write that as w squared squared. By doing so, if you have a square like this, then you can substitute in for it. So what we can do is write this as, we'll say, equals the integral, and this will be, I'll write it as sine squared x quantity squared dx. All right, so that's the integral. So now let's substitute what sine squared is. So it's going to be all of this. Okay, so that will be substituted. In fact, I can just duplicate that, huh? Okay, so that will be what's being squared. So that is now squared dx. And now we can multiply that out. It'll be a 1/4. We can see the 1/4 will factor out, and we'll just leave it. And then we have to multiply that out. So this equals 1/4 times the integral of 1 minus cosine 2x quantity squared dx. Went ahead and put in one more step there, which equals, and then we just expand it. So we expand that out, multiplying out the binomial, and that will be 1 minus twice the middle, 2 cosine 2x, and then plus cosine 2x, or cosine squared 2x dx. Okay. So now we can attempt to simplify this. So now this is into individual terms here. Our cosine squared 2x, we can simplify again using this formula. So let's take a look at what we're going to do next. These two are pretty good. That's done. This just uses a simple u substitution with a 2x. This will require another identity. So we will apply that identity there. So This equals 1/4 integral of 1 minus 2 cosine 2x. And then this will be plus, now let's be careful here because my I have cosine 2x. So I need to replace the 2x with the 4x. So basically I have like u is 2x. So my du is 2dx. So this half, so when you do this substitution, you get a half here and a half here, and this ends up being a 4. So it looks like this. So you end up having a half plus 1/2 cosine of 4x dx. Okay, this isn't needed yet. So now I go ahead and, so let me continue to simplify here. So I go ahead and add these together. And then I can essentially simplify this. So let me just go back to this one. So you're not doing integration yet. So you're not doing the derivatives or anything. You're not doing du and all that. Which all you're doing is this x is actually just 2x. So when you put it in this form, this becomes a 4x. So right here you put 2x, which becomes 4x. Okay, that's it. All right, so now let's continue this, and then you just got to work it out. This is a good place to stop, and you all work through this. Should be pretty straightforward to try that. All right, so you get 1/4, and then the integral, this becomes a 3/2 minus 2 cosine 2x plus a half cosine 4x dx, etc. All right. Now it's just a matter of applying basic integration. So when you have, and I'm not going to go through all these little details right here, but when you have u is 2x, your du ends up being 2 dx. So that half has to come underneath. So you end up with du over 2 equal to your dx. So that's what comes out in front. So this ends up being just gone, but this one will be 1/8 because you'll have that 4 down there. Okay, so try it, work it all out, be a little more careful than I am because you have time to do that. Let's see, what did I do here? What did I do here next? So 3/2. Okay, so now we can integrate. This is equal to, keep the 1/4, and then I just did the integration inside. So that's just 3/2 x minus sine 2x, because the integrating factor cancels the 2. And then plus, and now the integrating factor multiplies to give you the 4 times 2 is 8. So it's 1/8 sine of 4x. And then that'll be a plus c at that stage. And then you can distribute if you want. I mean, that's pretty much good enough right there. You can simplify it and distribute and get 3/8 x minus 1/4 sine 2x plus 1/32 sine of 4x plus your arbitrary constant. All right, so that's one case to power reduce the sine. The next case has sine and cosine in it, and then you do the same type of technique to power reduce. So let's take a look at that. All right. So next example. Suppose you have this. You want to evaluate the integral of cosine cubed x sine to the fourth x dx. And so this is where you can make a substitution to get something in the other form. So in this case, let's suppose we have u be sine x, then my du is cosine x dx. So by doing that, look what happens. You get this equal to the integral. So this is what you can do. You can basically take these and factor them. You peel off one of them to get your cosine x dx. So you can write this as cosine squared x sine to the fourth x, and then cosine x dx. Now this substitution is not going to help us yet right here, but what we can do with the cosine is rewrite that as in terms of sine. And we'll have everything in terms of sine, and then my u will be just u. So that's just 1 minus sine squared x, and then sine to the fourth x cosine x dx. Now my choice of u allows me to have all these in terms of u, and then that becomes my du right here. See it? That's my du. And then you have your correct u substitution. So that's the integral of 1 minus u squared u to the fourth du. So that's what we're after, is to be able to do something like that. So here's my du. And so now that's just a polynomial. You multiply it out and simplify it. So that's equal to the integral of u to the fourth minus u to the sixth du equal to 1/5 u to the fifth minus 1/7 u to the seventh plus c. And then now we substitute back, and we have 1/5 sine, I meant to write a 5 there, sine to the fifth x minus 1/7 sine to the seventh x plus c. Okay, so that's another kind of power reducing formula. And there are formulas for this to go from here directly to here. And I don't want you to do that. I want you to be able to choose your u to be sine or cosine and then apply the identities to get it in the correct form. That's what's really more important. Plugging in formulas is not the whole point here. All right, so let's do tangent and secant, and then that's pretty much covers these concepts, majority of it anyway. Okay, so evaluate the integral of tangent cubed x secant to the fifth x dx. So if you choose your u to be secant x, then my du is secant x tangent x dx. So we want to look for a secant x tangent x to do the whole substitution. So again, you apply some identities here. So what you can do is break this up into the integral, and then it's tangent So now, like, peel off one of those squares and one of those secants. So check this out. So you get tan squared x secant to the fourth x, and then now we saw what we were looking for. We're looking for that. So that's going to be my secant x tangent x dx. Now my choice of u is close because I still got tangent in there. So now you want to make that substitution for your tan squared. Tan squared is secant squared x minus 1, and then secant to the fourth x, and then the rest of my u, which is secant x tangent x dx. So there you go. That's what you're looking for. This guy is your du with your choice of u being the secant. And so you substitute and you end up with the integral of u squared minus 1. Then that's u to the fourth du. And then now you have just a polynomial to integrate. So it's integral of u to the sixth minus u to the fourth du. So that's 1/7 u to the seventh minus 1/5 u to the fifth plus c, and we substitute back. Substituting back, we end up with 1/7 secant to the seventh x minus 1/5 secant to the fifth x plus your arbitrary constant c. Okay, so those are the three main types you'll see is power reducing just one sine or cosine, using those, possibly the identities, of course, and then we're going to do the power reduce on cosine and sine, and then tangent and secant. So make sure you can apply these techniques to something similar. There's some formulas. You do want to practice the formulas. We'll get to that more in actually what we call tables. And there are some nuances to applying those formulas. But make sure you can do these basic types here. Okay.